Okay, my name is Hafni Afif. I will present my paper. The title is Comparison of Angle in 3D Model and Prototype using 5 DOF Inverse Kinematic. First of all, why I want to do this research. With the increasing human population today, it forces us to be able to increase human productivity in producing goods and necessities. Therefore, assistance from machines and robots is needed to increase the productivity. By using robotics, human can create technology that can increase massive productivity in human in producing necessities. A very important problem usually encountered in the study of robot is the inverse kinematic problem. Inverse kinematic need to be continuously developed and studied to support the development of robotics, which will help increase productivity in factory and manufacturers. Then, what is inverse kinematic? The simple way to explain inverse kinematic is it's a method for turning an object and shapes that depend on the structure, which is an articulated body. Articulated body can represent most animated figures such as human and animals, determining an appropriate joint configuration for which the end effector move to desired position, named target position, as smoothly, rapidly, and as accurately as possible. There are several studies that have been done previously. First, from Mr. Haswan and Mr. Feifei, have conduct research using inverse kinematic to imitate human movement. Both use MSK to capture motion given by the user data. Data obtained from the MSK is used to move the humanoid robot arm. In this research, inverse kinematic will use the data to determine the angle value of the motor. Next is from Mr. Andres and Mr. Joan. Has conduct the same research, but using a camera and the help of a special tools that has LEDs as the target for the robot to move the finger of the humanoid robot. In this research, inverse kinematic to used to determine the angle value of each joint. This value is obtained by knowing the destination to be reached by the end effector that have LEDs on the point, on the end point. Therefore, we think the need for a proper inverse kinematic solution and also the need to analyze an error in the prototype, we think we need to conduct a study that using a 3D model inverse kinematic model with 5DOF using 3D Unity and implement it on prototype using Arduino Uno and servo motor as a joint. Uh, there is our method and goals of the study. First, we will perform an inverse kinematic 3D modeling using 3D Unity, and then we apply the inverse kinematic on the prototype using Arduino Uno and motor servo. And the last, we take the angle value data from both 3D Unity and prototype and compare the result. The goal is to analyze the difference in the angle value to find the behavior error of the prototype so that it can be used to improve the success of the prototype in executing the inverse kinematic method better. Here's the 3D modeling we make. There are 4 spheres and target spheres. Sphere 1 will act as the shoulder of the human robot arms. Sphere 1 will be able to move from on X and Y axis from 0 to 190 degree with a counterclockwise movement. And Sphere 2 will act as an elbow of a humanoid robot. It will move on Y axis from 0 to 190 degree with a counterclockwise movement. Sphere 3 will act as the worst of the humanoid robot, where it moves from with X and Y axis path and from 0 to 190 degree with a counterclockwise movement. Sphere 4 will be the end of effector. It will point the endpoint and it will act as index finger on the human robot. Target sphere will be the destination point. The location of the target sphere will determine the movement of the 3D modeling. The inverse kinematic method will take the coordinates of the target sphere and use the coordinate data to be the angle value of that will be moved on each spheres or joint. Next is the prototype design. Here we use cardboard as the body part of the robots, and we use 5 motor servo to make it move and act as a joint. Servo 1 will move according to y-axis from 0 to 190 degree, and servo 2 will move to x-axis from 0 to 180 degree. The servos, servo 1 and servo 2 will act as a shoulder of the humanoid robot. It will act as spear 1 on the 3D Unity modeling. Next is servo 3. It will move according to y-axis from 0 to 180 degree. The servo will act as an elbow of humanoid robot. Servo 4 and servo 5. Servo 4 will move according to x-axis and servo 5 will move according to y-axis, both from 0 to 180 degree with a counterclockwise movement. The servo 4 and servo 5 will act as the worst of the humanoid robot. There is the result of the experiments. We have 5 recorded data. On the left table is the 3D modeling and the right table is prototype. We try at first experiment, we try to put the target in a place that doesn't make the servo move too much from the starting point. First experiment is to move the robot. Is it able to move the desired position or not? We can see on the first experiment, sphere 1x move with 26 degree on the modeling. Sphere 1y is 0 degree. Sphere 2y is 56 degree. Sphere 3x is 90 degree and sphere 3y is 90 degree. On the prototype, you can see it can move with a little bit gap. Servo 1 has 25 degree. Servo 2, 0 degree. Servo 3, 55 degree. Servo 4, 90 degree. And servo 5, 90 degree. After we doing the first experiment, we try on the second experiment to move the target position a little bit wider on the worst, so we can see the worst can move according to the desired position or not. We can see on the sphere 3x on the modeling, the value is 26 degree and sphere 3y is 154 degree. And on the prototype, we can see servo 4 uh, have 25 degree and servo 5 is 155 degree. On the third experiment, we try to move the elbow and the shoulder a bit wider from the starting point. In here, unfortunately, the prototype cannot unable to execute the inverse kinematic well. We can see on the third experiment, on the modeling, we try on the sphere 1y, the value is 53 degree, and sphere 2y is 160 degree. Meanwhile, when we apply it on the prototype only can move on servo 2 is 10 degree and servo 3 50 degree. On the fourth experiment, we move the target to make the elbow a little bit to bottom or a little bit down. We can see on sphere 2y, the value is 18 degree. On the prototype, we can see and at servo 3, it's 30 degree. Because of this failure, this big gap on the servo, on the fifth experiment, we tried the calibrating position, which is this position is the natural position that we can see is the motor servo is able to move to according position or not. On the fifth experiments, we can see on the 3D modeling, sphere 1x is 90 degree, sphere 1y is 90 degree, sphere 2y is 90 degree, sphere 3x is 90 degree, and sphere 3y is 180 degree. But we can see at the prototype, servo 1 only able to move to 40 degree, servo 2 only able to move to 30 degree, servo 3 only able to move to 20 degree, servo 4 still can move to 90 degree, and servo 5 can move to 180 degree. This is the angle value differences table. Here we can see at the first and second experiments, the servo still can work properly. When we try to move the worst or just a little bit movement on the shoulder and elbow. But when the third experiment began, unfortunately, the prototype unable to make it the elbow and arm to move a little bit wide. There are a big gap on the angle value between the 3D modeling and prototype. We can see at servo 2 and servo 3, servo 2 have 43 degree and servo 3 have 66 degree gap. And because of these servos, servo 2 and servo 3, servo 5 also failed to move to the desired position because there is no room anymore to make the servo 5 move. Next, at the fourth experiment, even though it's lower rather than the third experiment, but we can see the servo is unable to move to the desired position when we try to make it move a little bit to down to bottom to the lower uh, coordinate. When we try this experiment, we can feel there is a vibration on the servo 2 and servo 3. It indicate the servo still trying to move to the desired position, but it cannot, it's unable to move anymore. We think it's because the high workload that the servo do, the servo done at the third experiment, it make the servo cannot work properly at the fourth experiment. And this is the reason why we want to do the calibration position at fifth experiment. And here we can see at fifth experiment, when we do the calibration position, the data show us that the servo 1, servo 2, and servo 3 is unable to do the work anymore. It's unable to move to desired position. We can see at servo 1, it's have 50-degree differences, and servo 2 have 60 degrees differences, and servo 3 it 70-degree differences. After this fifth experiment, we still try to do another experiment. We try to move the target position again and apply it to the prototype, but unfortunately, servo 1, servo 2, and servo 3, it's unable to execute the inverse kinematic and move to the desired position anymore. Even when we still trying after that, the servo 1 and servo 3 cannot move anymore. So we broke the servos because the heavy workload on the body part and the servo. After these experiments, we conclude that the inverse kinematic can work properly on 3D modeling, but unfortunately, the prototype unable to work properly due to the heavy workload on servo. Therefore, we recommended to use a servo motor that can work with a strong workload so that it can move accurately with the desired angle value. Or we can try to remodeling the prototype the, to changing the joint model so the servo is not directly installed to the body part. It would be better if the joint was moved by a pulley system that is used string or cable that is used to pull the body part using a servo motor. I think that's all for me. Thank you.